Hello, everybody. Welcome back to another discussion dynamics. Today we will do work energy method again. Let's see where we are on our timeline. We are here. So again, work energy method. I think for the last time, next discussion we will start new topic. And today we will do example number 1 and 2 and maybe 3, because 3 is exactly the same as number 2. I don't know why. It's exactly the same. Okay, so we're gonna do example number 3 in 60 seconds, basically. So example number 1 is work energy method. Example number 2 is power and efficiency. And just a reminder, if you wanna let me know what you think about my work, just please go to this website, and they will tell you what to do. Okay, you have time till Sunday. Yeah, it's not obligatory. You can do it if you want. That's it. And tell me what you like. Maybe tell me what you would like to change. I read it, yeah. And I actually, this is helpful, yeah. I sometimes change something in these discussions, yeah. Okay, and from now on, I will also send you these empty boards, yeah, because for example, this drawing is like quite time consuming to draw right now, yes. So before our discussions, I will send you these so-called empty boards, so you have all of those drawings before, okay? Other than that, please familiarize yourself with the problem statement before we start our solution. Okay, I sent it to you earlier, yes, so I'm not gonna spend time on that. So what do we have in here? We have two bodies again, yeah, we have system of particles, we have little body that weighs mass m, we have big body that weighs twice as much. We have force F acting on little body, and we have friction force between these two, on these two surfaces, yes? And our bodies are connected with the pulley structure presented in the picture, yeah? Yeah, that's almost all, because they also told us that system starts from rest. Yep. And they told us to express velocities of these two bodies as a function of absolute displacement. Yeah, so last discussion. So on Wednesday we talked about relative displacement. Yeah, there was like delta rel. Yeah, do you remember? Today we will just have similar situation, but we will talk about absolute displacement. That's why I put this marker here, that red marker, do you see? So this is exactly place where our two bodies start. Yep, and relatively to this marker that is constant in place, constant in position, that this body moves s, little body moves s to the left, and that implies that our big body will move 2s to the right, yeah. So s to the left, 2s to the right, yeah. Why? Because of the pulley structure, yeah. So we will just express v1 and v2 in terms of this s, okay? Okay. Since we are in this topic, work energy methods, we're gonna use this expression for 17th time this semester, yes? And second step will be finding these 5 values, T1, V1, T2, V2, U1, 2, non-conservative. Okay. I'm not as good as you in dynamics, so I'm gonna just start with easy stuff, yeah? System starts from rest, so that was not a funny joke, yeah? Sorry for that, yeah. T1 is 0, yeah, because system starts from rest, yeah? System starts from rest. Yeah, it's like my grandfather's joke, yeah, kind of, sorry. Okay, T1 is 0. Now, question to you guys. Let's find potential energies. Do we have springs in the system? No. Do our bodies change elevation? No. 0. and 0. Okay, now kinetic energy at the end. We have two bodies moving, yeah? So we will write in here 1/2 of first body V1 squared plus kinetic energy of the other body. Yeah, so it will be 1/2 times 2m, because the other guy weighs 2m, times V2 squared. Yeah, and we introduced two unknowns right now. Yeah, we introduced V1 and V2. Let's reduce it to only one. Okay, so we have let me scroll it. So we have one rope attached to this body, and we have two ropes attached to this body. Okay, so I think I can write in here V1 is equal to V2, but where I'm going to put where I am going to put number 2? I don't know. I think I will put V2 here. Yeah, here. Yeah. Okay. Great. So that's how we reduced one. Get rid of. That's how we got rid of one unknown. Let's plug this one here, and if you do it, you will end up with such expression: 9 divided by 2 m v1 squared. Great. 80% of the problem done. Yeah, because we found this, 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 and this. And now, this is actually the interesting part of that problem, because I decided to do it in a little bit different way that maybe you would like me to do. I mean, so what I'm getting at, on Wednesday, do you remember? On Wednesday, we kind of expressed this value, yeah, when we look at the relative motion between two bodies. Do you remember that delta L? Okay, so why don't we today just look at the same problem, similar problem, but from the perspective of each body separately? Okay, so you at home, try to look at the entire system. Okay, and try to write this for the entire system. At home, try to find. I'm dyslexic, sorry. Find U12 non-conservative for the entire system at once, okay? But today I would like to express it in such way: U12 non-conservative for body 1 plus U12 non-conservative for body 2, okay? That property is called additiveness. And you clearly see why, yeah? Because we can express that work as sum of works, yeah? So work of the entire system can be expressed as work done on one body plus work done on on the other body, yeah? It's clearly, work is an additive quantity, in other words. Work is an additive quantity. Okay, I really talk too much today, sorry, yeah? So without talking more, yeah, U12 non-conservative of body 1. This is our goal right now, okay? So how we were doing that? Aha, I think that we were starting from FBD, yeah? FBD for body 1. FBD for 1. And I think that body 1 has this pulley structure attached here, yeah? So I want to go for easy forces. So I'm going to go for mg. What else is easy? I think that there is normal force, yes? Normal force. N12, let's call it, yeah? Because this is normal force acting between these two bodies, yeah? And just in case you forgot, I'm going to scroll up the board. Body 1 is this little guy. Body 1 is this little guy. Okay? So what other forces do we have in here? I think we have 3 more forces. Anybody wanna tell me? Yeah, Vincent? Friction, yeah. And which direction our body will go? This way or this way? That way. Okay, so friction will be acting this way. Exactly. So this is our TF. TF, can we call it TF12? Okay, because this is TF between two bodies. Okay. And you're right. Yeah, DS goes this direction. DS goes this direction. There are two more forces. F, exactly. Yeah, this guy. F, and also tension in the rope. Yeah. So we have 2T. Yeah, we have two ropes attached to our body. Yeah. And this is trajectory, of course. Trajectory. Okay. So I think everything is non-conservative besides mg. Yeah, everything is non-conservative besides mg. So whoa, a lot of writing. So we'll have u12 of f plus u12 of 2t plus u12 of tf12 plus u12 n12. Okay, as I promised, we are not going to do that anymore. What's that value? 0. Perfect. Why? Because of the perpendicularity. Yes, you can write that. Perpendicularity. Yeah. Yeah. Just a little digression. Guys, I cannot regrade your scores. Yeah. However, you can if you want to talk to a grader, you can always consult your exam with me. Yeah. I cannot regrade it, but I can just tell you if you are thinking correctly. Okay. Yeah. Let's go back to our problem. Aha. So now we have these three integrals. Yes. So we must write integral, let's say, from beginning till end, AB. Later, this A and B will be replaced by numbers, okay? But let's keep A and B here right now. F times ds plus the same integral from, of 2t times ds plus integral from A to B, tf12 plus times ds. Okay, let's do first integral. I think f is constant, yeah? Let me see. Check this out. They told us a constant force f. Yeah, we like to integrate stuff that is constant, yeah? And before integrating, I think we should find integration bounds, yeah? Anybody? Maybe somebody who was like silent the entire semester would like to tell me what numbers I should put here and here? Yeah. Marcus, you were very active at the beginning. Now for a couple of weeks you're silent, yeah? Do you want to go for it? Or if you don't want to, it's fine. Yeah. Yeah. No. Yes, of course. I'm sorry, yes. Yeah. So the question is, yeah, what I should put here and here. Yeah. And this is the body. What's the displacement? Yeah. So S in here and 0 here. Yeah. 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 Okay. Thank you. All right. And F points in the same direction as ds. Yeah. Awesome. So it will be F S. Just that. Yeah. How about 2t? T is also constant, yeah? And that 2t points in the other direction than ds. So that would be minus 2ts, yeah? How about friction? Friction always points in the other direction, yeah? So that would be minus tf12 ds. Dang, I forgot to find tf12, yeah? But you guys already know what that is, yeah? So we can clearly write that we are in kinetic friction. And I already assumed that it's constant, yes? Kinetic friction, because we have tf12 is equal to mu k n12, yeah? and you guys can clearly see that this must be equal to mu k mg, yeah? Why do you know that? Because of this sum of forces, yes? Along this direction, you can clearly see that n12 minus mg must be equal to 0, yes? Because of our trajectory, yes? Yeah. So I hope you don't mind, guys, if I just put here, instead of TF1, I will put here mu k mg times s. Sorry, times s. Whoa. Really, I'm talking too much today. I'm sorry, I don't know why. Yeah. Anyway, there will be time for questions. So we are done with finding work done on body 1. This is the answer. And we have 90% of the problem done. Before starting 10 remaining percents, there is time for questions. Dhruv. Thank you. Exactly. If you look at the entire system, so at home, do you see this sentence? Yeah. And so if you look at the system as a whole, yeah, you can ignore tension. However, right now, I decided, I don't know why, but I decided to show you how to do it if you look at each body separately, okay? And actually, the punchline will be your question. The punchline will be, look, guys, indeed, work of internal forces is 0. Does that answer your question? Yeah. Awesome. I hope it makes sense. Anybody else? How does it look so far? Are we on the same page, guys? Yeah, cool. So let's do that remaining 10%. Let's do it. So now U12 non-conservative of body 2, yeah? Okay, and again, similar steps. FBD for body 2, yeah? So that would be that long body, this body. FBD for 2. Okay, so I'm gonna go for easy forces, okay? So I believe that body 2 weighs 2 mg, right? Yeah. And also there will be normal force. Let's call it N2, yeah, because this is normal force between body and the ground. I think there will be tension in the system, yeah? Okay, and I think there are 3 more forces, yeah? Anybody want to help me? Yeah, Kevin. Force of friction from 1 and 2 on the top. Perfect. And wait a second. So TF1 was pointing this way. So that means I have to flip the direction, yeah? Here, exactly. Continue, please. Awesome. TF12. And our body goes this way, yeah? This is our trajectory. Our body goes this way, so that will be ds, let's call it 2, okay? Because this ds2 is different than the previous one, yeah? This that will be twice larger. ds2 will be twice larger than ds. Yeah, so if ds points this way, you are right, because that will be tf, I know, tf ground, or tf ground, let's put tf ground. Okay, ground. Or tf2 maybe, yeah, just for simplicity, tf2. Anything else? You good, yeah. And you are always active, yeah. Anybody else? There is one more force acting on the structure, yes. Christina. Perfecto. And that force was acting up here. Yeah, that force was acting up here. So I have to flip the vector, yeah. And 1, 2. Thank you, guys. Thank you so much. Okay, we are ready to write our expression. Uh-oh. Okay, so how many non-conservative forces we have in here? 1, 2, 3, 4, 5. Yeah, because everything is non-conservative besides 2mg. So we will have U12 of TF12 plus U12 of TF2 plus U12 of T plus U12 of N12 plus U12 of N2. Okay, guys, two last expressions are 0. This is 0 and this is 0. 0 and 0. Why? Because of the perpendicularity. Yeah. Thing. Great. So instead of 5 things, we just do 3, which is good. Okay. So let's write our integrals. Again, from a and b. You don't have to write that a and b. Later, we will replace it with numbers. Okay. TF12 times ds2 this time, plus integral from a to b tf2 d ds2 and scalar product, plus from a to b t times ds2. Okay, before solving our integrals, let's replace that a and b with some numbers. Okay. Any volunteer? Is there anybody who wanna help me? Yeah. Hi. Trevor, maybe you. Yeah. Yes, exactly. It's this time it will be not from 0 to s, but from 0 to 2s. Thanks, man. 2s, 0 to 2s. Yeah. Why 2s? You are wondering? Because if we look at this picture, you can clearly see that our big body, this body, moves 2s. Yeah. In absolute coordinates. Yeah. In absolute. Yeah. It moves 2s towards the right. Thank you, guys. So again, TF12 and TF. Let's find them. Kinetic friction, yeah? Kinetic friction. So I think that TF12 we already found, yeah? I can basically copy paste this expression. So that would be mu k mg, mu k mg. And now TF2 will be mu k n2, yeah? This vector. That vector that acts between the ground and our big body. I'm wondering what that n2 is, okay? So in order to find n2, we should write sum of forces in the y direction. So what do we have in there? We have minus 2mg minus n12 plus n2. And by the way, this is equal to 2m ay. But because of the trajectory, this is 0. So that's why this will be 0. And you guys told me that n12 is mg. Yeah, this one will be mg because you told me that here. You told me that. Here. Great. So now we can see that our n2 is equal to 3 mg. Yep. This is our reaction force between ground and big body. And it's constant also. This is constant. Great. So, and this is constant as well. So that will be mu k 3 mg. This is constant. This is constant. And we like why I keep saying that this is constant, because we like to integrate things that are constant. Yeah, you can do it like that. Okay, just like that. So what do we have in here? We will have mu k mg 2s And I forgot about the minus, yes? Yeah, but not really. Okay, and in here we will have mu k 3 mg times 2s, yeah? Also with a minus. And tension is also constant. So in here we will have T times 2s and with plus, yeah, because T points in the same way as ds2. Great, so I can put plus in here. All right. That's it. I mean, that's it, yeah. We have 100% of the problem done, yeah? This is our work done on body 2. Okay, so we have this thing we can select as found. Okay, next step, plug everything back in here. And before I do that, are we on the same page, guys? Any questions so far? Am I talking too fast today? Or is the pace is good? Yeah, okay, cool. Okay, so let's plug everything back. So I think that we had T1 equal to 0. I think that also our potential energies were 0. And in here I can just plug these things we found. So I can plug this in here. And this is quite big, so I'm gonna just make it smaller. And also, so that was energy on body 1. And also I have to put this thing in here. Plus energy done on body 2. This is also too big, so I'm just gonna do it like that. Okay. And this is equal to T2, which was, if I remember correctly, 9 divided by 2 mv1 squared, and v2 was 0. Okay, so we ended up with a long expression, yes? So long it cannot fit here in one line, yes? And Dhruv, thank you for that question. I did all of that stuff just to show you that indeed this cancels with that. Okay, work of internal forces is 0. Okay. Questions? Yes, Trevor? Yeah.
Since we chose different directions of ds in body 1 and body 2, would you have to subtract the second body from the first body? Since they're pointing in different directions instead of adding them?
No, not really. That's a good question. No. The answer is no, because my answer will be twofold. Okay, first one, I solve problems in magnitudes. Okay, that's why in these expressions, I usually 99% of the time I just put variables. Okay, I don't care if they have to be multiplied by minus or plus. However, this is my style of solving these problems. I developed that style by my own. I am aware that there is different style of other people that somehow they know where to put minus or plus. It's too complicated for me, okay? And this is recorded. I might eliminate that from the video because I don't want everybody to know that. But honestly, I do not understand how they do that, yeah? And I try to develop style that is as simple as possible, okay? At least for me. That's why I don't do what you want me to do. I mean, I don't do that subtraction or addition, yeah? However, I also think that that question does not apply to what you have in your mind. Do you know why? Because we compute work done on the body for each body separately. So in other words, that body has no idea that the other body exists in the system. Okay, that body only knows that it moves this direction and that something is pulling it, and but it does not know what that is. Okay, so I just solved that work for that body only, and I found the value. Then I go to that body, and I found work of that body separately. Yeah, that body has no idea that the other body exists. Yeah, so I just found that body, work done on that body, and the work is some of that things. Okay, so I think that the second answer is better than the first one. Yeah.
So like work is just discrimination. It doesn't depend on direction that you're moving.
Yes. Yeah. It depends, but that direction is associated only with body 2. It has nothing to do with this. Okay. Okay. Yeah. I don't know. I'm kind of not happy with my answer, but think about it. Think about it. We can talk later. Okay. Yeah. Yes.
Just to add to that question, could it be said then that I mean we're already taking care of like directions in each FBD?
Yes.
So in the end, it's like we can just plug all the works in because in the FBDs we're already taking care of the plus and the minuses.
Even earlier, even here, I took care of directions. Yeah. So usually, what I do, I solve problems in magnitudes, and I obtain usually positive number. Usually, yeah, sometimes negative, yeah. But then I say directions are presented in the picture. Okay. This is the magnitude of that quantity. The direction is on the picture. This is what I do.
Wouldn't it 2v1 equal like minus v2?
If you are in a different school than me, yes. I mean, so I am in that school. I usually do that. I know that some people put minus here. I know that some people do it. I don't do it because I just solve them in magnitudes, and again, directions are shown in the picture. Yeah. There was a question here also. I think Mia, Marcos, or John got the question. No? Oh, sorry. Okay. Any other question? Okay, guys. So sorry for that longer break. But we are one step from solving, yes, because they ask us to find velocity 1 expressed as a function of position, yes? So that's exactly what we have in here. We have just this expression with velocity, and this is our position. Yeah? So we can just write that v1 is equal to square root of 2 divided by 9m times f minus 9 mu k mg times square root of s. Exactly, this is some function of position. Okay, this is our answer. And they also ask us to find v2 as a function of s, yeah? That's easy because v2 is equal to 2v1. So I am going to just write 2 in here. I'm just going to copy paste that expression. Yeah. Okay. This is exactly like, I know, f2 of s. Okay, so this is the answer. Oh, this is the answer. Okay. How do you like that? How does it look like from your perspective, guys? Yeah. Hello. You can come in if you want. Yeah. Okay. Just don't make noise. Yeah. Okay. How do you like that? Yeah. It's digestible. Okay. So I don't know. Just try to look at that problem at home. Maybe if you have some questions, just hit me up during my office hours that are actually on Friday, today at 5 p.m. Every Friday. Yeah. Or just Piazza. Okay. Or go to other TAs to their office hours. Yeah. We offer office hours every day. Okay, what do you want to do? Do you want to ask a question or do you want example number 2? 2, okay, 2, okay. So in the other problem, yeah, indeed, work of internal forces was 0, okay? Yeah. And if you train enough, you will know, you will develop probably the faster way to solve these problems, yes? Please familiarize yourself with the problem statement before we start our solution. But we'll not spend time on you familiarizing yourself with the problem statement because I sent it to you earlier, yes? So you should come here and you should know what the problem is. So what do we have in here? We have one body this time, one body, M, and that body is on the incline. It has mass M, and it is pulled up the incline by this motor, yes? And it has constant velocity, by the way. And we know everything about motor. Yeah? We know what power it can generate, and we also know what is its efficiency, which is good to know. Yeah, because before we buy the motor, we should know what motor we need. Yes, and they ask us for maximum velocity. Yeah? They ask us what our motor can do. Yeah, how fast the body can be pulled up the incline. Yeah. All right. So these are two new equations, guys. You're gonna learn today. So efficiency is power out divided by power in. This is the expression, the new expression this semester, and also power can be expressed as force times velocity. Okay. So I would like you guys to tell me. What that power out will be. So power out will be some force times velocity, yeah, of our body. And what I would like you to do is I would like you to tell me what force I should put here, okay? But I will give you a hint. Let's do free body diagram, okay? And after seeing that free body diagram, you will tell me what I should put there. I bet you will, yeah. So let's do FBD, okay? FBD, even here. So we have mg acting on our body. But you know that I always go for easy stuff, yeah. Mg, we have normal force. We have friction, I believe. Yeah. TF, okay. And there is one more force, yeah, the tension, yeah, in the cable. I think there are no other forces, yeah. This is all. All right. So Mike is yours. By looking at this free body diagram, what, or even maybe at this picture here, what force I should put in here? Anybody want to help me? Yeah. And why, Colin? Exactly. This is how strong our gearbox is. Yeah. Thank you. That's all. Yeah. Thanks, man. Yeah. This is our power out. Yeah. This is power generated by the gearbox can be expressed with this expression. Okay. And our velocity goes this way. Yeah. Our velocity goes this way. I mean, it has the same direction. Yes. This is our velocity. Yeah. So I can write in here TV basically. Yeah. TV, because the angle is 0-ish. Yeah. All right. So let's find that t. Let's find that t. Let's write equation of motion along this direction. Okay. Along this direction. So sum of forces along this direction. Okay. What do we have here? We have n. What I'm talking about? Of course, not along this direction. Yeah, along this direction. Sorry, guys. This direction. Excusez-moi. Sorry. So we have t minus tf and I have to project this guy, yeah? So we'll have these two vectors. This guy will be mg cosine, and this guy will be mg sine theta. So we have minus mg sine theta, and this is equal to ma, I don't know what is this direction. Last time I used some Greek letter, okay, and everybody got confused. So I'm gonna use this direction. This direction is xi, okay, or choose any letter you want. So that will be xi. But xi is 0, yeah? Why? Because velocity is constant, yeah? Okay, so we can clearly see that our t is equal to tf plus mg sine theta. And again, tf is our kinetic friction, yes? So it will be mu k times n. So that would be, so tf will be mu k mg cosine theta. Okay, so we found our expression for t. T is equal to mu k n, mu k mg cosine theta plus mg sine theta. Perfect. So we found our t. Okay, so that's, many of you are confused with that c. Let's use alpha, okay? Because I know that alpha, okay? That is alpha. Okay, so now let's plug everything that is in the boxes into our equation, okay? So let's plug this thing that is in the box here, and this thing, let's plug in here, okay? And we'll end up with oh shoot, sorry. P out epsilon is equal to mg mu k cosine theta plus sine theta velocity. And they ask us to find velocity. V is equal to mg mu k cosine theta plus sine theta. P out epsilon per in. Yeah, sorry guys, per in, not P out. That's all. That's the problem. Yeah. So when it comes to recipe for power and efficiency problems, I don't have any recipe. Yeah, I just go for this expression. I just go for this expression, and I figure stuff out. Yeah, I don't know. Every problem will be different. Yeah, so just go for sure. Write those two expressions, and then let's see what will happen. Yeah, guys, it's already 11:50. Do you mind if I steal 40 seconds from your time? 40 seconds only, okay? So this is answer for this example number 2. However, example number 3, if you want, please familiarize yourself with the problem statement. Don't do it. Yeah, this is exactly the same problem as example number 2. Exactly the same. They don't ask us to find V, they ask us to find mu k. They only ask us for that. Yeah, this is the only difference. So what I'm gonna do, I'm gonna copy this. I'm gonna copy this. Yeah. And instead of like P in epsilon, instead of that, they just told us to use P out, okay? So just start with that expression and just find mu k, okay? So after some algebraic play, you will end up that mu k is equal to 1 over cosine. Yeah, I'll do it quickly. P out mgv minus sine theta. And this is the answer to that problem. Yeah. Okay, thank you for your patience. Enjoy your weekend. Bye.